In this video, we're going to talk about the kinetic model of a gas. So the kinetic model of a gas is going to help us explain and predict sort of macroscopic properties such as pressure and temperature, but we're going to explain that on the microscopic scale in terms of the motion of the particles. And so we have to make a series of assumptions in order to use this model effectively. First assumption is that gas contains a large number of identical molecules and they're constantly in random motion. The next assumption is that the number of molecules is sufficiently large for statistical averages applied. So you're thinking in terms of this mole scale, times 10 to the 23 particles. The volume of individual molecules is negligible compared to the volume of the gas, so we're not considering the actual size of the molecules in our model. Molecular motion is isotropic, so that means that in any given direction, there are the same number of particles traveling in that direction. And that applies to all directions in the three-dimensional space of the object. Collisions between molecules and with container walls are perfectly elastic, which means that kinetic energy is not lost. There are no intermolecular forces except during collisions, so the molecules in the gas are not attracted to each other. The collision time is negligible compared to the time between collisions, so they're just in contact for very brief periods of time. And so this simulation comes from the Falstad simulation. The link is in the description. But I think it really highlights the kinetic gas model here. And so they've color-coded the speeds of the molecules. And so the bluer, purple molecules are moving much slower. But when they gain energy, they become more hotter colors, with yellow being the fastest moving particles. But what you can see here is all the particles are moving in kind of random directions. They're bouncing off of each other and off of the walls. There's an average speed, but they're not all traveling at the same speed. There's a lot of different speeds happening here. And molecules can gain and lose kinetic energy depending on the collisions, but the total kinetic energy remains the same at all times. So now we're going to get into how do these assumptions lead to explanations of macroscopic observations such as volume, pressure, and temperature. So for a gas, it'll always expand to fill all available space. And when you have a rigid container, so a container that can't change shape, the volume remains fixed. But we can do experiments and other things in flexible containers. So we have like balloons, pistons, syringes. So these are containers where the volume can change. And so volume is not always static. It just depends on the type of container. So a temperature of a gas is a measure of the average kinetic energy of its molecules. And we saw this equation in earlier units. So the average kinetic energy of a single molecule is proportional to the temperature multiplied by the Boltzmann constant. And so if the temperature goes up, the average kinetic energy goes up, which means the average speed goes up, so then the molecules are moving faster. Pressure of a gas comes from collisions of the gas molecules with the walls of the container. And so in the next slide, we're going to explain in detail how do we get an even pressure from molecules colliding with the containers. And so we're going to have to go through this step by step, but this is a very important explanation, and this is the level of detail that's required of us when we're talking about pressure of a gas. So when a molecule hits a wall, it undergoes a change of momentum. And then the rate of change of momentum produces a force on the wall. And that's from Newton's second law. We know that F is equal to delta P over delta T. And so when the collision occurs, we get a change of momentum, so that's producing a force. This force causes a pressure on the container, because we know that pressure is equal to force per unit area. And so these molecules are producing a force, which produces a pressure. Now, why is the pressure even all around? And you notice that like when you have a balloon, you can feel the pressure on different sides and it feels all the same. Well, it's because there's so many, and it's because the motion is isotropic. And so we saw that earlier. This means that in any given direction, there are the same molecules traveling in that direction. So that means that the force creating the pressure is even throughout. And so that's why we feel an even pressure in those containers. Last, we want to talk about internal energy. Now, normally we define internal energy as the sum of the random kinetic energy and potential energy of the particles. And when we learned about phase changes, we learned that kinetic energy is related to temperature and the potential energy is related to the phase change. Now, in the ideal gas model, we're assuming there are no intermolecular forces, which means that there is no potential energy. So that means the energy, the internal energy of an ideal gas, comes only from the kinetic energy or the motion of the particles. And so we're ignoring any sort of potential energy. And we can do that because these molecules are so far apart and they're moving so quickly that the potential energy is negligible. And so that's why we're allowed to say there's no intermolecular forces. But this definitely wouldn't work for liquids or solids because they're much too close together. They have a high potential energy. So that was a summary of the assumptions and the macroscopic interpretations that come from the assumptions. And so this lays the foundation for the ideal gas law and other things that we're going to study further.